Okay, so center of mass of a continuous distribution using integration. By application of definite integration. So first and foremost, we had seen that for any continuous mass distribution, we can take a differential or very small element of mass dm, and if that element is placed at a position vector r in respect to our coordinate frame, then the position of the center of mass of the system, the vector position, becomes integration r dm divided by total mass. So we can convert this to the coordinate scalar equations, that x coordinate of the center of mass is integration x dm divided by total mass, y coordinate is similarly integration y dm divided by total mass, and similar formula for z. Okay, so this is the general concept. So what we are doing is, for a discrete particle system, we are taking summation mr divided by total mass. Okay, so for a discrete particle system, we had seen this was summation of r into m divided by summation m. So that summation is now completed by integration. So in a continuous mass distribution, what we do is we replace this mass of this particle as a differential mass, and therefore we replace the summation with integration, and the denominator is of course total mass m. So that's how it becomes integration rdm, like that. Okay, so now about the sort of standard protocols or the standard solving methods that we use for executing these integrations in different situations. Okay, so we saw that depending on whether the mass distribution is a linear distribution, okay, that is, the mass is divided or is distributed over a certain length of a thin kind of material, like a metallic wire, or a thin rod or a rope or something like that, or it is divided, the mass is distributed on a surface like a plate, okay, or a bowl or something, a thin shell, or the mass is distributed over a three-dimensional volume, which is any solid three-dimensional object, any solid rigid body. Accordingly, the mass element dm is either taken as a differential length, lambda being the mass per unit length into TL, or a differential part of the surface. So sigma is mass per unit area into a differential area dA, or a differential part of the volume. So it is density into that differential volume dV. So this is the most important thing, that we are able to further understand that dm has to become a length element in the case of a linear distribution, a surface element in terms of a surface distribution, or in terms of a volume element in case of a three-dimensional volume distribution. And once we are able to make that decision, then according to the exact geometry of the system that we are dealing with, we take the shape of that element, okay, and we proceed further. So as we do examples, you'll understand more how to execute this. Okay, so the couple of examples we had done was, we had seen a thin uniform rod with a variable linear mass density or variable mass per unit length, and how to use the integration there. Then we saw how to calculate the position of center of mass of a thin uniform wire which is bent into the shape of a semicircular arc. Okay, so we had seen this standard example in the previous class. So if we have a thin uniform semi-ring, by uniform we mean that mass per unit length is uniform, then we saw that the center of mass lies on the symmetry axis, which, as the distance from the center of curvature goes, if the radius of the semi-ring is r, then the distance OC was 2r by pi. So I told you that this is a standard example that you have to memorize as a formula also. But at the same time, you should also be aware of how to actually find the position of the center of mass using integration. And this is how we found that position. Okay, so let's continue from that point today here. Any doubt in this part so far? Please let me know. We'll discuss that point again. Okay. Yes.
Sir, I didn't understand the mass distribution part, like the bottom half which you wrote.
The mass distribution, if it is linear or it is distributed over a length. Okay. So for example, when we take a thin uniform rod, which is bent into some kind of shape, like the case of the semi ring over here, the mass distribution is what type of a distribution? It's a linear distribution. No? It's not distributed on a surface or a volume, but it is distributed over the length of a certain object, right?
Yes, sir.
Okay. Similarly, if you take the case of, let's say, a square plate, a thin square plate of mass. So how the mass is distributed? It's distributed on a surface, no? It's not distributed
Yes,
over a
sir.
length. So those are surface distributions. Or for example, you take a hemispherical bowl, okay, which is open from top. So again, the object is three-dimensional, but the mass is not distributed over volume because it's a hollow shell. The mass is distributed over the surface of the bowl. So that will also be a surface element, surface distribution. Understanding me?
Yes, sir. Thank you, sir.
Whereas any solid three-dimensional object like a solid cylinder or any arbitrary shape, also like a solid rock, that's an example of what kind of distribution? Volume distribution, right?
Yes, sir.
Okay. So now when we are
Sir,
extending this, yeah,
sir, what is that 2r by pi? That thin uniform
is the distance
semi.
between the center of mass and the center of curvature, beta. We have done the
Ha,
derivation of this
ha.
formula in the last lecture. No? We
Yes,
saw that
sir.
the center of mass will be somewhere on this symmetry y-axis, right?
Symmetry of y, yes.
ये distance d अगर लेते हैं ना, from the origin here, which is the center of curvature, to C, which is the center of mass, that distance d is equal to 2r by pi, right? No?
Yes, sir.
So O is the center of curvature of the semi-ring, whereas C is the center of mass. Okay. So that we can clear this. Okay, so let's, in fact, since we are on this subject, let's begin with a variation problem of this same example. Now, instead of semi-ring, let us assume that what we have done is we have bent that shape, or we bent that thin wire that we had. We have bent it into a circular arc of some other type of angle. Okay, so suppose, or suppose we had a thin ring like this, okay, the full ring, and then what we did is we sliced out a portion of this ring. So first of all, let us say this is our horizontal diameter, this is our vertical diameter. And now suppose what we have done here is we have completely sliced out this much part. Okay. So we have now a thin wire, which is like a circular arc, but it's not in the shape of a semicircle because it does not subtend 180 degrees at the center. Rather, what it is doing is that if we look at this here, this is a total angle of, let us say, 120 degrees. Okay. So in this example, we are looking at a thin uniform arc of radius r and subtending an angle of 120 degrees at the center of curvature. So basically it is 1/3 of a full ring. Now full ring is 360 degrees at the center. This is 1/3. So we have to locate the position of the center of mass. Center of mass is position. Okay. Okay, so obviously we will make use of this concept of center of mass, that position of center of mass is integration r dm divided by total mass, where here dm will be which type of element? Dm will be lambda dl type of element because this is a linear distribution of mass. Okay, this much is clear to begin with for all of you. Yes. Okay, now can anybody tell me if there's any axis of symmetry?
Yes, sir.
Yeah,
60
what is the
degrees.
axis of symmetry? The 60-degree angle, no? The angular bisector.
Yes, sir.
Okay, so the center of mass will lie on that axis of symmetry, you know. So what we'll have to do is we'll have to reorient our system of axis, or take the axis of symmetry as some kind of axis for ourselves. Okay. Just a moment. Let me redraw the diagram. Okay, so hope everyone has understood this business of axis of symmetry. Okay, so if this was the center of curvature, where it was subtending 120 degrees, so if this was the center of curvature, then what we'll have to do is we'll have to take the angular bisector of this total angle, which is 120 degrees. We have to take the angular bisector of this as our symmetry axis. We have to take like an angle like this. Okay. So this is now suppose our y prime axis and this is our x prime axis, such that this angle is equal to this angle, which is 60 degrees. Then we know that our center of mass will lie somewhere here. Right, this is clear again to everyone. Okay. So let me just make the diagram easier for myself by assuming that I have turned my head. So I'm seeing this like this now. So it's a little bit easier to analyze this. Okay, it's actually the same thing. So I've turned my head a bit like this. So this is my angular bisector now. Okay, this is my y prime axis and this is my x prime axis. Okay. But remember, of course, that my original x and y axis given in the diagram, original diagram is this. So ultimately, after getting the position of the center of mass, I'll have to once again give the coordinates of the center of mass in terms of xy system, not x prime y prime system. But first, it will be convenient for me to work out in terms of x prime and y prime. So my center of mass is sitting somewhere here. Okay, so I need to find the coordinate. So now we will use the same method as we had done earlier. That suppose we take at some angular position theta from here, we take a small element. Okay, so it is subtending a small angle d theta. So the length of that element will become r d theta. So this element has a mass dm and a y coordinate like this. So say y prime. So that dm element, which is lambda dl, will become, now what will be the lambda over here? It will be total mass divided by the total length of the arc. Okay. Now the length of the arc will be what? Angle into radius now. Okay, this is the arc length. So angle here is how much? 2 pi by 3. Okay, and into radius is r. So that is how this will become 3m by 2 pi r. Okay. Or you can see that it is 1/3 of a full circle. So 2 pi r by 3. So our lambda is this. Okay, so lambda is m divided by 2 pi r by 3. It's 1/3 of a circle, and the dl is r d theta. So here my dm is becoming 3m upon 2 d theta. This is the mass of that element. Okay, and the y coordinate of that element in the diagram you can see is going to be how much? In this diagram for me, it is going to be this. Okay, this is the y coordinate of that. So it's going to be r cos theta. So now from this we can see that the y coordinate of the overall, or rather the y prime coordinate, we'll call it. Okay, the y prime coordinate of the center of mass of the system will become integration y prime dm divided by total mass. So integration of r cos theta into 3m by 2 d theta. But what about the limits now? Can somebody tell me what the limits are? I'm integrating from a to b here, let's say. Okay. So lower limit mein a mein theta ka value what will take as
30.
But with sign plus or minus?
Sir, 0 to 2 pi r by 3.
Nahin beta, see what I have taken theta as. I have not taken theta as the angle from the x-axis. I have taken this angle here as theta, na? Tabhi to y coordinate kya liya? R cos theta, na? Got my point, na? So see, if this angle is theta,
150 to 30.
nahin. See what theta is beta. It's the angle with the y prime axis. See in the diagram, na? So what is the angular position of this point with respect to the y prime axis? It is minus 30 degrees, no? Sorry, minus 60 degrees, no? The total is 120, isn't it? And what about the angular position of this point? Plus pi by 3. Is it clear? Okay, taking this angle with the vertical line here, y prime, as your theta. If you take this angle as theta, then the angular position of the leftmost point A and the rightmost point B are going to be minus 60 degrees and plus 60 degrees. Now, I hope this point is clear, people. Okay, so this is going from minus pi by 3 to pi by 3. Okay, so we have 3 mr divided by 2 cos theta d theta, going from minus 60 to, sorry, minus 60 is pi by 3 to plus 60. Okay. So please complete this integration and tell me how much we are getting this as. Yes, Adinath, can you do the calculation once more and send me, please? Yes, very good, Adinath. Now the answer is correct in terms of the y coordinate. Okay, and finally you can just convert it to an xy coordinate by using trigonometry. Okay, come to that also. So as you can see, this will become 3r by 2. M is getting cancelled, and then cos's integration is sine from minus pi by 3 to pi by 3. So that is 3r by 2 sine 60 minus of sine of minus 60. So that is 3r by 2 into root 3 by 2 minus of minus root 3 by 2. That's how that becomes root 3 inside the bracket. So this is this. Okay, now once I've got this, I can convert this to xy coordinates. Okay, because if I go back to my original diagram, this one, this was my y-axis, this was my x-axis. Now the semi-ring, the arc was over here. So okay, this was the situation. So now we have taken this angular bisector as our y prime axis.
Sir,
Yes.
sir, dm should be 3m by 2 pi into d theta, right?
3m by नहीं 2 pi नहीं बेटा, pi cancel हो गया. See here, lambda में 2 pi r है, but there's r d theta for dl, no? Getting this, no?
Sir, can you repeat?
Oh, sorry, pi is there. Yes, yes. There is a pi. Yes, that's correct. Okay. So there'll be an additional factor of pi everywhere. Yes. So please make that correction, people. Okay. Here, dm has a pi in the denominator. This one. Okay, from here to here. R gets cancelled. Pi is still there. Okay. So you just have to put an additional pi everywhere. Okay. So pi here, pi here, pi here. Yes. So there is finally 2 pi in the denominator. Okay. Okay. Now coming back to this diagram. So now our center of mass is over here. Okay. And this angle you can see is 60 degrees. And we have just seen that this distance OC is equal to 3 root 3 by 2 pi r. So if the center of mass's coordinates are xcm comma ycm, okay, you can see that the x coordinate will be cos 60 into this, and the y coordinate will be sine 60 into this. Yes, very good. So x coordinate of the center of mass in that system will become 3 root 3 r by 4 pi, and y coordinate of the center of mass will become 9 r by 4 pi.
Sir, can you show the question for a second?
Yeah. So see, this was the original example here. Okay, Adinath, we integrated from minus pi by 3 to pi by 3 because you can see in this diagram better here. Just pointing out. Look at this particular diagram, this one. Huh? So understanding now, any particular point P here, I'm locating it as the angular position theta equal to theta with respect to which axis? With respect to the y prime axis. Now.
Yes, sir.
Okay, so in that respect, what will be the angular position of the point A? It is at 60 degrees with respect to the y prime axis, but on the other side, it is anti-clockwise 60 degrees.
Yes, sir.
Whereas the point B is clockwise 60 degrees. So we are taking clockwise as positive here. Because this is theta, we are taking this like this. Okay, so this side is negative theta, this side is positive theta, right? So that's why minus 62 plus 60.
Okay, sir.
Okay, now like we've developed the formula for this, now there is one general formula, which I will just put up the formula for you. You can do the derivation of this formula yourself later when you're revising this part. But the important thing will be to basically memorize this formula so that we can use it directly in problems. Okay, and that is if we have, instead of a given angle or instead of a particular angle like 60 or 30 or 90 or 180 or whatever, if we have any general case, then how do we find the position of the center of mass of that kind of general case? So we have this situation, and now let us say this is the bisecting axis of symmetry, and this is the center of curvature, suppose. So we have a situation like this where now this angle is equal to this angle, which is alpha by 2. So we have basically a thin circular arc, okay, of radius capital R, and angle, total angle subtended at the center is alpha. That is this. Okay, then the center of mass will lie on the symmetry axis at a distance from this, from the geometrical or from the center of curvature, such that so center of mass C lies on the angular bisector, which is the y-axis, at a distance d equal to OC, so that distance equals to the general formula r sine alpha by 2 divided by alpha by 2. Where alpha should be in radians. So this is the general formula. So for example, for semi-ring, we had that alpha would have become pi. So d becomes r sine pi by 2 divided by pi by 2. So that is 2r by pi. And that is what we had derived earlier also by integration. For 1/3 of a ring, which is the example we just did above, alpha is equal to 2 pi by 3. So d should become r sine pi by 3 divided by pi by 3. So that is 3r by pi into root 3 by 2, or 3 root 3r divided by 2 pi. And again, that is the formula that we got. But now for any other general example, so suppose we have a situation where we have 1/6 of a ring. So our alpha is equal to pi by 3 or 60 degrees. So D becomes r sine pi by 6 divided by pi by 6. So here D will become 6r by pi into half. So 3r by pi. Okay, so it will become this kind of situation. Or we have the case of, let's say, a quarter arc. So alpha is equal to pi by 2. So D will become r sine 45 degrees divided by pi by 4. So 4r by root 2 pi. So any given sort of situation, we can calculate the position of the center of mass. Okay, now moving on we will come to our first example of a surface distribution and how to calculate position of center of mass by using what we can call a surface integration. That is, we are going to integrate over a surface instead of over a length. Okay, so our variable of integration is instead going to be dA, or a differential area. So the particular example we will start with is the example now of a semi-disk. Like we've taken a thin uniform disk and sliced it exactly into half. Okay. So we want to calculate the center of mass or find the position of center of mass of a thin uniform semi-disk. So imagine we had a full disk like this, and then we have sliced it into half. Okay. So this is like a three-dimensional picture of the disk. Imagine semi-disk. So if you see this in 2D, so we've got this. So once again, there is an axis of symmetry and all that. But before that, this is what kind of distribution? This is a surface distribution. So when we do the integration, we'll have to take the differential mass element as sigma into dA. So let's say the mass of the semi-disk is m and this radius is r. So here this radius is r. So once again, we take the bisector as our y-axis, the center of curvature of the semi-disk as our origin. So in that case, we can see that sigma will be total mass upon total area. So area of the semi-disk surface is pi r square by 2. And what should dA be? It should be a differential surface area element. Okay. So one way we can slice this surface into elements, differential areas, while keeping note of the fact that the y-axis is an axis of symmetry, is we can slice it like this into thin strips. Like this. So each of these strips is a differential area. It's a small amount of area of the total. Okay. So this we will take as thin strips. Okay. Parallel to the x-axis. Because here y-axis is the symmetry axis. So each of these thin strips that we have sliced, it has a thickness which will become dy. Okay, its center of mass is at the y coordinate y over here, but we can take this length as x. So the total length becomes 2x. Okay, so the area of this strip will become length into thickness. So the length can be written as 2x and the thickness is dy. And further, when we apply Pythagoras theorem here, this radius is r. Okay, so this can be written as okay. So this is the area of that strip. So mass of that strip, sigma dA, becomes 2m upon pi r square into 2 times square root of r square minus y square dy. Okay. So now y coordinate of the center of mass of the system, because y axis is an axis of symmetry. So center of mass lies on the y axis at a position which will be given by this formula. Okay, so that here will become y multiplied by this factor divided by total mass. Now what about the limits? What should we take as the limits of integration here?
0 to r.
Yes, we'll take from the largest strip at the bottom where the y coordinate is 0 to the smallest strip at the top, which is almost like a dot. Actually, it's not like a horizontal strip. Its length is tending to 0, but its y coordinate is becoming r. So 0 to r becomes the limit for integration. Okay. So just make a note up to here. Then we'll discuss about how to do the integration. So I'll give you a hint on what to do for the integration also. Just note down up to here first.
Sir,
Yes. Now, any idea about the integration? How to proceed here?
sir, can we also take instead of parallel to x-axis, can we take strips parallel to y-axis?
You can do that also, but then the strips will be of thickness dx, okay, and length y like that, and you will have to write the individual y coordinate of that each strip as y by 2 now. You understanding my point? If the strip is of vertical length y, then the y coordinate of its mass dm will be located at where? At its center of mass.
Yes.
So it's going to become a slightly more complicated situation in that case.
Good.
Okay, now let's see how to do this integration. So what we can do is, see, we have got y outside and we have got r square minus y square inside the square root. So notice that if you take r square minus y square as a new variable like z square, okay, then differentiation of this will tell you that minus 2y dy is equal to 2z dz. That means what we've got outside y dy can be written as minus of z dz. So I'm just rewriting this like this. This can be written as, okay, this can be written as integration of square root of r square minus y square into y dy now, from y equal to 0 to y equal to r. So now if I substitute the quantity inside the square root, which is creating all the trouble, if I substitute that as z square, then you can see the quantity which is outside y dy just becomes minus z dz. So the integration in the next step will become very simple. It will become like this. This whole square root term will just become z, okay, and y dy is just minus z dz, okay, and this will go, now the limits I'll have to interchange, okay. So the lower limit was y equal to 0, but now notice that when y is equal to 0, what is the value of z? Z is equal to r, and upper limit was y equal to r. Now because of this relation here, okay, because of this substitution, you can see that okay, when y is equal to r, z is becoming 0. So this will become minus 4 upon pi r square into z square by 2, or let's write that in another step. Z square dz integration from z equal to r to z equal to 0. So minus 4 upon pi r square into z cube by 3 from r to 0. So here the upper limit will in fact be 0. The lower limit will be r cube by 3. So the bracket leaves us with minus r cube by 3, absorbing the minus sign outside, and we are left with the standard formula 4r by 3 pi. We have r cube in the numerator and r square in the denominator. So the position of the center of mass with respect to the center of curvature of the disk, that is now given by this formula 4r by 3 pi. So coming back to what is the significance of this final formula, it's like this, that if this is our semi disk, okay, then
Sir,
Okay, so this is also one of the standard formulae that you will have to memorize, people. The position of center of mass of semi-disk. Yes, Adinath, the reason why we change, actually it's not like we change the limits, but we change the variable of integration. The limits in terms of variable y, अगर y के terms में देखूंगा तो limits क्या है? Lower limit is y equal to 0 and y equal to r. But when y is equal to 0 at the lower point, what is the equivalent value of z? Because now we are changing the variable of integration to z now. So that is coming from this
yes,
relation, this relationship between y and z. So you can see that when y is equal to 0, r square is equal to z square. No? So z is equal to r.
yes, sir.
So that's how
And
we are
at
doing.
upper point, Z is R.
Yeah. Okay.
Okay, sir.
Okay. So now we had discussed that one variation of this would be that instead of taking horizontal strips or strips parallel to the x-axis, we can take vertical strips, and you can try that method yourself. Now there is another interesting variation which actually makes this easier to execute as an integration, and that is utilizes what we have done before this one. Before we came to the position, the center of mass of the disk example, we had seen the center of mass of a semi ring. So instead of slicing it into straight strips, now can't we cut it into semicircular rings, thin semicircular arcs? You can do that also, no? Okay, so imagine that I'm not slicing it using straight lines, but I'm slicing it using semicircular arcs. So I can slice this whole disk into a collection of sort of concentric semi rings like this. So this is another easy method of finding the position of the center of mass. In fact, if you look at the standard derivation in H.C. Verma, or for that matter, Resnick-Halliday, you will find this method because it's the integration part which becomes easier in this. Okay, so that's another method. So alternately, our element, surface element, okay, can be taken as a thin semi-ring. So if that ring has radius, I mean semi-ring has radius r and a thickness of dr, okay, then that area of that semi-ring will become length into thickness. It's like we've taken a rod of length pi r and thickness dr. Now we bent that rod into a semi-ring like this. Yes, okay, so the area becomes this. Okay. So mass of that becomes sigma dA. So that becomes 2m upon pi r square into pi r dr, or 2m upon r square into r dr. This becomes the mass of that. Okay. Now this semi-ring's own center of mass is located here. Okay. So that we'll take as the y coordinate, and that is 2r by pi. This is the position of TM's center of mass, not the semi-disk center of mass, center of mass. So now y coordinate of the center of mass of the semi-disk, that one will become integration y dm divided by total mass. So this particular semi-ring is now replaced with a particle of mass dm, but at which y coordinate? At 2r by pi. So 2r by pi is the y coordinate of that particle, which is equivalent to that semi-ring, into its mass, which is 2m by capital R square into r dr. Okay. Just a small correction here, this should be capital R square. Capital R is this radius of the semi-disk. Small r is the radius of the semi-ring, the differential element that we're taking. So anyway, and what about the limits now? The limits will be taken from the smallest ring at the center to the largest ring at the circumference. Okay. So I'm just giving you the final solution. So 4m by pi r square. Okay. That m will also get cancelled out, but now we are left with a very simple integration. R square dr going from r equal to 0 to r equal to capital R. This is also a very effective way of demonstrating that the center of mass of a semi-disk Okay, so now this is an example of a surface element, as I told you. Okay, let's take another example. Now let's move on to a surface which is not in a two-dimensional plane. So it's not in a laminar kind of situation. It is a non-laminar surface or a three-dimensional surface. So that particular example we will take is again going to be one of our standard formulae. We're going to look at the center of mass of a thin hemispherical shell. Okay, so basically an open hemispherical bowl, that kind of situation. So we're going to find the center of mass of such a body. Okay, so let's say this is the open mouth of the hemisphere. So basically we've taken a thin spherical shell and spliced it into half. Okay. And once again, take the origin at the center of curvature. And this is an axis of symmetry. Let us say the base of the bowl is lying like this. Okay. So this time, let's take this as our X and Z axis, whereas the Y axis is the axis of symmetry. So the center of mass will lie somewhere like this. So again, we have to find YCM by using this formula. But again, you can see that this shell, it is a surface distribution. Hence, we should take dm, because it's a surface distribution, as a sigma dA. Okay. But the question is, what should the dA be over here? What kind of surface element we should take? So how we can slice
The
this?
ring.
Yes, exactly. Very good. If we slice the hemispherical bowl, imagine you're cutting it into thin slices, but using a plane to slice it, which is parallel to which plane? Parallel to the XZ plane. Then we will get thin rings, right? And those thin rings are all having the y-axis as the axis of symmetry. So it is going to be easy to understand that we can replace those thin rings with equivalent particles on the y-axis. So this point here is our origin. We're taking this downward axis as our y-axis. And this is our z-axis, let's say. And this is our x-axis. So if we slice it using a plane parallel to the XZ plane, so parallel to this open mouth, then we are slicing it into thin rings like this. So this should become our differential element. So this dA should be thin rings sliced with a plane or sliced by a plane parallel the XZ plane. So now if such a ring is having a radius of small r, okay, and a thickness of dl, so that ring's area dA will become its length, which is 2 pi r, into its thickness, which is dl.
So can't we say DL is equal to dy?
Sorry, come again. Can't we say?
DL is equal to dy.
Very good question, but there's a reason why we cannot say that, beta. Because if you imagine this in 3D now, that ring is like, imagine it like a ribbon which is taped onto the spherical surface. So is the thickness of the ribbon projected on the y-axis or is it on a curved surface?
It's a curved surface.
So that is why now when we take the thickness of that ribbon into account, we cannot take it as dy. Dy will be like the shadow of that thickness on the y-axis, which will be less than dl actually. Okay. So instead what we'll do is we'll take dl as a small arc, okay, with respect to the center of curvature O. And again, we'll express dl in terms of d theta, the angle it subtends. Okay, so just make a note of this diagram first and get comfortable with the explanation here. Then we will come to the technicalities of how we'll express small r and dl. As you can see, small r, the radius of the rings are also variable quantities. They're going to range from capital R to 0. We are taking slicing all the rings from the top to the bottom. So you can see the rings radii are progressively going to decrease as you go down. And the thickness of each ring is the thickness on this surface here, not the thickness on the y-axis, but the thickness on this surface. This is the thickness. Okay, so now let us look at how we will execute the integration. And actually, through this example, we'll also look at another interesting calculation. Apart from center of mass, we can also use integration to demonstrate why the surface area of a hemisphere is 2 pi r square. Okay, I'm sure all of you are aware that surface area of a hemisphere is 2 pi r square. Full sphere is pi r square, like that. So hemisphere being half of that. So we can give a proof of that particular formula also. Now coming back to this, so now imagine we are slicing a thin ring somewhere here. And since we are referencing it to this center of curvature O, so we're taking this as our y-axis. So now what we will do is we will take the position where this ring is present with respect to this y-axis as theta. So the ring's thickness itself also subtends a small arc. So the thickness of the ring dl will become r d theta. Okay. So this thickness, this angle is d theta. Okay. And the radius of this ring, which is small r, will come from trigonometry. It is capital R sine theta. So the area of that ring, which is circumference into thickness, becomes 2 pi r sine theta into r d theta. This is the area of the ring. Yeah, in case you have taken the angle with the x-axis as theta, then you'll get it as cos theta. Okay.
Yes.
And eventually you get the same result, but the way you set up the integration, the limits will be reverse of what I am getting, because I am taking the axis with respect, the angle with respect to the y-axis. Okay, so now before we get into center of mass, actually, we can see something interesting here. This is the thin ring. So if we now want to calculate the hemisphere's area, surface area, we have to just integrate dA now. So we'd end up integrating 2 pi r square sine theta d theta, okay, according to my value of theta over here. So I'd start from the lowest ring at the bottom, for which theta would be 0, and take the uppermost ring at the top, for which it would be pi by 2. So the total surface area should become, take the constant 2 pi r square outside, integrate sine theta from 0 to pi by 2, and that is unity. So this is a proof that surface area of a hemisphere is 2 pi r square. Surface area of the hemisphere. So this is aside from our purpose over here, which is to find the center of mass. Okay. So now using this result or your general knowledge about surface area, we can also see sigma is m upon E. So total mass m divided by 2 pi r square. So once I know sigma, I also know that that thin ring, it has a mass dm of sigma into dA. So that sigma is m upon 2 pi r square, and dA is nothing but 2 pi r square sine theta d theta. Okay, so I can see now that this is m into sine theta d theta. This is the dm. Okay. Now, where is the y coordinate of this ring? What should I substitute as the y coordinate? The y coordinate is this. Okay. So for the thin ring, the y coordinate is r sine theta. Okay. So this is the mass, this is the y coordinate. So now for the hemisphere, or for the hemispherical shell, the y coordinate of the center of mass will become integration y dm divided by total mass. So just replace y with r sine theta, dm with m into sine theta. Oh, one mistake, it's r cos theta. Just a moment. So this will be r cos theta. Okay. And the limits will be from, once again, 0 to pi by 2. So now we are replaced with okay. So now you have to just complete that integration, which is an easy integration. You can just use the trigonometry double angle formula. Sine 2 theta is 2 sine theta cos theta, or you can use a simple substitution because cos theta is the derivative of sine theta. Okay, so you should be getting the answer as that's correct, Adinath, r by 2. Anybody else? On the y-axis, it's at r by 2. So the coordinates are as you have written them. So we'll get y coordinate of center of mass as r by 2, because when you do this integration, you can see it is basically integration of sine 2 theta by 2 from 0 to pi by 2. So again, you can do it this way, take the half outside, and sine 2 theta's integration will become minus cos 2 theta divided by another 2. Okay. And this is going from 0 to pi by 2. So take that other 2 outside, so r by 4 into minus cos pi minus of minus cos 0. So 1 minus of minus 1. So that's one way to show that it is r by 2. The other option is you can also do like this, that integration of sine theta cos theta. You can substitute sine theta as z. Cos theta d theta becomes dz. So the integration becomes z dz, which is z square by 2 plus c. So sine square theta by 2 plus c. So that's another way you can do this. So integration of sine theta cos theta from 0 to pi by 2 will become sine square theta by 2 from 0 to pi by 2. And that will give you half. So that's another way we can do this alternate method or this method. But whichever way we do, finally, the result that we get. Okay. So this is another of the standard formulae that you have to keep in mind for position of center of mass. Semi-ring, semi-disc. Okay, general formula for circular arc. Okay, then what was the next one that we saw? This one, hollow hemispherical shell. Okay. And one more we'll do today, which is a solid cone. The position of the center of mass of a symmetrical solid cone. So that will be our first example of a volume distribution. We'll discuss about that next. Just make a note up to this first. Let me know in case of any doubt with the steps of integration, especially substituting limits and all. You have to be extra careful while doing these type of problems. Okay, so people hope this example is clear. Okay, now we come to the final example for today for these standard cases of center of mass. Okay, and in this one, we'll discuss about center of mass of a solid symmetrical cone. Now, just for convenience, which you'll understand when we execute the calculation, we will show it in an inverted situation, the cone. And we will reference the center of mass instead of to the center of the base. We'll reference it to the apex of the cone, which is this point here. So once again, if we join the apex of the cone with the geometrical center of the base, we have the axis of symmetry. We take this as a y-axis. The base of the cone is lying actually parallel to the XZ plane. The y-axis is the symmetry axis. So we can visualize that the center of mass will lie somewhere here. And we can also understand from the shape of the cone that if the height of the cone is h, then the center of mass should lie at a y coordinate, which will definitely be greater than h by 2, right? Because it's becoming thicker as you go up. Okay. And this base radius is r. Keep that in mind. Okay. So now this is a 3-dimensional volume distribution. So it's a solid cone. Okay. So it's a volume distribution. So the position of the center of mass will come in terms of the y coordinate of the center of mass. But here, what is dm? It is going to be a volume element. So it must be fairly obvious what kind of volume element we should take. But can somebody just tell me what is the volume element we'll select? The logically, yes, we should take thin discs. So we'll again, imagine that we are slicing the cone using a plane parallel to the XZ plane. Okay, but only because it's a solid cone, unlike the hollow hemisphere earlier. This time when we slice it, what kind of shape we will get of the thin elements? They will be solid thin discs instead of rings. Okay. So that means that we have to consider the volume of these discs and not the surface area. And for considering the volume of the disc, we will have to consider the thickness which is projected along the vertical axis, that is the y-axis. So this time we will take the thickness of these discs as dy, not like dl on the side, not the inclined thickness, but the vertical thickness. So if we slice a disc over here, we will now have to consider not the side thickness, but the thickness projected on the side length L, but on the vertical thickness, which is dy. Okay. And this here is the y coordinate of the disc. This is the radius. So this is a thin disc. That will be our volume element. So its volume will become what? Its volume will become surface area into thickness. So pi r square into dy. So now we can see that as far as the radius is concerned, the radius is a function of y, which we can calculate like this. Sorry, this is r, small r, and this is y. Now at the same time, this is capital R. This here is capital R, and this here is H. So we have similar triangles. This triangle and this triangle, we can R by H is equal to R by Y. So we can use this. Yes, very good. So and use this relation that it will be R by H into Y. So the volume of that disk you can write as so. Now the interesting thing is, before we get into center of mass, once again you can also use this expression to show that the volume of a what is the volume of the cone? What is the formula? No one? 1 by 3 pi r square h. Do you remember seeing this formula somewhere in class 10th or whatever? Maybe 9th. Okay, so this formula can be shown from here. You can just integrate for all the disks. To do this integration, that gives you this. Okay. So anyway, now the mass of that disk. So the sigma for this, sorry, the rho, the density will be total mass upon total volume. So m upon 1 by 3 pi r square h. Into the volume of that element. So that's r square by h square pi into y square dy. So dm here is becoming how much? 3m upon r square will cancel out, h cube into y square dy. So now the y coordinate of the center of mass of the whole thing, you have to substitute this and carry out the integration. Okay. So as I was telling you, it's an interesting aspect that it is independent of R. As long as there's a solid cone, there's also a solid cone with the same height. The position of the center of mass will be the same for both of them. Okay, so now we have completed the derivation for almost all the standard examples of position of center of mass of various shapes of, various geometries and various shapes of rigid bodies, various types of distributions. So having done this, you will have to make yourself a table of these values and keep in mind the direct formula, because we'll be using this in other type of application questions later. Okay. So next lecture, we will go back to also examples of conservation of linear momentum in the situation where we have a system of many bodies where the individual bodies are in motion. And from there, we will get into collisions, which is a special case of conservation of linear momentum, okay, which is the final and the most important part of this chapter of system of particles, the applications for collisions. So we are coming to that over the next couple of lectures. Okay. So that's it for today's session, people. Wish you all the best and have a nice day and stay safe.
Thank you.
Thank you, sir.
Thank you, sir.
Okay.
Bye, sir.
Sir,
Yeah. Tell me.
sir, can you send the notes of previous lecture?
Yeah, I'll have to get them sent better because they are on the digital whiteboard. So it has to get transferred and all that. So yeah, let me see how soon I can get that arranged. Okay.
Okay, thank you, sir.
Okay.
Sir,
Yes.
sir, why did we take dy here instead of dl?
Yeah, because here we are considering a solid disk, na beta. So see what is happening is now when you slice that cone into thin discs, basically each disc is looking something like this. Each disc is not a perfect disc in that sense because it is a little bit truncated from the side, isn't it? Like this. It's more like a frustum of a cone, na, each disc.
Yes.
But now we are concerned with what? The volume of the disc. Na? We are not concerned with the surface area of the ribbon, but we are considered with the solid volume. So we have to consider this thickness, not this thickness. Understood? This is the difference between dl and dy.
Sir, so in the case of a hemisphere, if we wanted to calculate the center of mass of a full hemisphere, like solid.
Solid hemisphere, yeah. So again, we would slice it into discs, and we would consider the volume of the discs. Not, we won't slice it into rings, which was the case of the hemispherical shell today. So when we are considering the surface area, we have to consider it like a ribbon, which is on that surface. So the thickness of the ribbon is which one? The one which is lying on the surface. So it is dl. What my point?
Yes, sir.
Whereas when you slice it into discs, solid discs, then which thickness you have to consider? Not the thickness on the curved surface or on the side surface, but the vertical thickness of the disc, because you're concerned with the volume of the disc.
Yes, sir.
Okay, so that is why your volume integration and surface integration are done with slightly different technique, okay, in this kind of situation.
The dl and dy, can we take them almost equal?
Sorry, come again. DL and DY
almost equal.
नहीं बेटा, उनमें एक फैक्टर का डिफरेंस है, a sin theta cos theta type of difference.
Sir, cos theta ना?
हाँ, है ना, depending on which angle you're taking, with the vertical or the horizontal. So for example, if the semi-vertical angle for this cone were to be 37, then your dy and dl have a factor of this thing, 3/5. You're getting my point, so you will get a big mistake in the answer if you replace dy with dl.
Yes.
Because see, you're not just considering the dl, you're integrating, so you're considering the cumulative length. So there is a huge difference in the cumulative length of the side L versus the cumulative vertical height H.
Yes, sir.
Okay, so this is something one has to understand and be careful about in integration. Okay.
Sir.
Yes.
Sir, if we, in that last question, if we take a cone whose height is still the center of mass, sir, then the mass of that cone and the section left above will be equal?
Okay, how can the what did you say? If you take what at the center of mass, the apex of the cone.
Sir, apex is same, but the height of the cone is still the center of mass. It is a smaller cone as compared to the actual cone, sir. And the part left above the frustum.
Acha, you saying that we slice the cone that way.
Yes, sir. Yes, sir.
Then we will be left with a frustum and a smaller cone, no?
Yes, sir. So will their mass be equal or there is no such relation?
No, there is no such relation, beta, because it is, see, in fact, you can understand that the mass will not be equal. Because the distribution of mass is not happening that way, no? It's thinner on one side and thicker on the other side, no?
Yes, sir.
No? Okay. So it will not be such that one side will have equal mass m/2 and the other side will have equal mass m/2. Okay.
Yes, sir.
Okay.
Thank you, sir. Bye.
Okay.